Hey humans, and welcome back to my science studio. In our last lesson, we talked about complete and incomplete combustion reactions. But today we're going to be learning a brand new type of chemical reaction called single replacement reactions, also known as single displacement reactions. Both terms essentially mean, the same thing. In this video, you'll learn how to identify a single replacement reaction, how to predict the products, and how to use the activity series. So, let's get started. A single replacement reaction follows this general pattern where you have A reacting with BC to produce B and AC. And what's happening here is that element A replaces element B in a compound. And you see, most of the time you'll compare two metals, where A and B are metals, or you'll compare two halogens. In that case, it'll look a little different, but you'll see what I mean. It keeps the general pattern. The big idea here is, you guys, that A will only replace B if A is more reactive than B. And to figure that out, we have to use the activity series. Now, you are not expected to memorize this at all. Always use the one your teacher or professor gives you in class for your exams. But this is my activity series, and it ranks the elements from most reactive at the top to least reactive at the bottom. So just keep in mind, sometimes it's written horizontally, sometimes the most reactive is at the bottom. So just pay attention to your labels and know how to read the table that your teacher gives you. And notice that metals have an activity series, as shown here, and halogens also have their own reactivity order as well. If you remember, halogens are a family in the periodic table, and they are found in group 17 or group 7A of the periodic table. Now let's try a worked example together. Here you have Zn, zinc, reacting with copper 2 sulfate, right? CuSO4. And you're trying to predict the product. The first thing you want to do is check the activity series. And I see here that zinc is above copper. So I know the reaction will occur. The second step you want to do is to predict the products. You see, the idea is that A has to be stronger than B. Zinc is your A, copper is your B, and the sulfate's your C. So now we know that A is going to kick out B, right? Zinc is going to kick out the copper. It's going to replace it. But remember, sulfate is SO4 with a -2. And zinc has a +2 charge. It's fixed. So when you cross the charges between zinc and sulfate, the +2 and the -2 end up canceling each other out. So you end up getting ZnSO4, also known as zinc sulfate. And Cu is left by itself. And it's a solid, it's a metal. This is very important. Notice that metals, like in this example, are written alone when neutral. Do not write Cu2+. That's wrong. You should not have any ions in your balanced equation or in your chemical reaction. Just write Cu. Now let's try a halogen example. Here we have chlorine gas reacting with NaBr, or sodium bromide, and you're trying to figure out the products. One little side note I want to make: anytime you have any of the 7 diatomic elements, right, your mnemonic, have no fear of ice-cold beverages, you have to show that it's diatomic by writing the subscript 2 next to the element. Chlorine gas is one of those 7, and it exists on its own naturally as Cl2. This 2 is very important when you balance the chemical reaction later on. So just keep a note on that. And in this example, we know it's a single replacement, right? But we're not comparing two metals this time. We're comparing two halogens, the chlorine and the bromine. And we're trying to figure out whether or not the chlorine is strong enough to kick out the Br. So you go to the table and you notice that chlorine is more reactive than bromine and will replace it. Essentially, chlorine will form a bond with Na. So now let's go back to our reaction. We know that the reaction will occur. So what you do is you combine the Na and the Cl. We know Na is a +1 charge and Cl is a -1 charge. Cross the charges and you get NaCl. And we kicked out the bromine, but you cannot write Br by itself. Remember, bromine is one of those 7 diatomic elements. So you have to write the subscript 2 to denote that there's 2 atoms of bromine naturally bound together. Now that we have a reaction, now we got a balance. On the left side, we have 1 Na, and on the right side, we have 1 Na as well. On the left, we have 2 chlorines, and on the right, we have 1 chlorine. And on the left, we have 1 bromine, and we have 2 bromines on the right side. So the first thing I do is I try to balance the chlorines, right? So if I put a 2 as a coefficient in front of the NaCl's, that changes the number of Cl's to 2. But that also changes the number of sodiums, because now I have 2 sodiums. So if I put a 2 now in front of the NaBr, that gives us 2 sodiums, but it also changes the number of bromines. But lucky for us, we have 2 bromines on the left and also 2 bromines on the right. So now we're good. What about this next one? We have silver, Ag, reacting with potassium nitrate, or KNO3. The first thing you want to do is see if the reaction will occur or not. So in this example, we're comparing 2 metals. We're comparing the silver and the potassium. So remember, your silver is your A, your potassium is your B, and your NO3, your nitrate is your C. You're trying to see if A is stronger than B to kick it out. So you go to the table. And if you notice, silver is less reactive than potassium, not more. So no reaction will occur. Guys, if it can't kick it out, guess what? Nothing happens. You literally write no reaction as the products. Now on your test or your quiz, maybe your teacher will trick you and write in multiple choice, that is an answer choice D, no reaction. Don't be afraid to circle that choice if there really is no reaction happening. Don't just start making products when the reaction could not possibly happen. Okay, you guys, I have these 3 practice problems here. I urge you to pause the video, try these on your own first, and when you're ready, go ahead and press play. Okay, so in this first question, we have magnesium, right? It's a metal, and it's reacting with sulfuric acid, also known as H2SO4. And right off the bat, I recognize this as a single replacement because I have A plus BC. So that means I'm going to make AC plus B, right? Here we're comparing the magnesium and the hydrogen, right? Magnesium is your A and hydrogen is your B. And on the activity series, we see that magnesium is above hydrogen. So the reaction will occur. We can predict the products now. Now, magnesium will form a bond with the SO4, with the sulfate. So let's write the charges here real quick. Magnesium is in group 2A of the periodic table, okay, and is more likely to form a +2 charge. And SO4, or sulfate, is a -2 charge, right? These are fixed charges that we're dealing with. They don't change. When we cross the charges, whenever you have opposite charges that are the same magnitude, so in this example, you have a +2 and a -2, they end up canceling each other out. So we end up getting MgSO4, also known as magnesium sulfate, plus H2, or hydrogen gas, essentially. And the reason why you don't just write hydrogen by itself is because this is one of the 7 diatomic elements. So you, again, if it's a diatomic element, you have to write the subscript 2 if it's not bound to anything else. If it's by itself, you give it the 2. This does not apply to metals like, for example, magnesium. Mg does not have a subscript 2. Okay, it exists by itself as Mg. And looking at it here, it looks to me like it's already balanced. So we're good. Now the second problem, we have I2 or iodine gas reacts with potassium chloride or KCl. And we're trying to figure out the products. Well, again, the first thing you want to do is see whether or not the reaction will occur. And you'll notice that we're not comparing 2 metals here. There's only 1 metal here. There's only 1 potassium. So we're comparing 2 halogens. And we're trying to see whether or not the I is strong enough to kick out the Cl and form a bond with the potassium. So if you go to the activity series for the halogens, iodine is less reactive than chlorine. So guess what? No reaction will occur here. Let's try this last problem. You have aluminum, right? A metal, reacts with iron 3 nitrate or FeNO3 parentheses with a 3 on the outside. And we're trying to figure out the products. Well, first of all, I recognize, again, this is a single replacement. I have A plus BC, and I have to make AC plus B. So we're trying to figure out if the aluminum is strong enough to kick out the Fe, the iron. And it turns out from the activity series that aluminum is more reactive than iron, and it'll kick it out and form a bond with the nitrate. So the reaction will occur. Now, let's make our product AC. Our A is our aluminum, and it has a +3 charge. And our C is our nitrate, which has a -1 charge. When you cross the charges, you end up getting Al parentheses NO3 with a 3 on the outside. That 3 on the outside came from the aluminum. But when we brought it down to become a subscript, it's very important to write a parentheses around the nitrate whenever that subscript that you drop is greater than 1. Okay? Because in this example, that 3 tells me that I have 3 nitrate ions present, which is the same thing as saying 3 times the amount of oxygens, which is 9. 3 times 3 is 9. And 3 times the amount of nitrogen, which is 3. So just keep that in mind, and it's very useful when balancing. I prefer to keep the polyatomic ions together and treat them as a unit, but some people like to split apart the atoms and count the oxygens and the nitrogen separate. That's totally okay. Both methods work. I just prefer to do a little bit less math, but that's totally up to you. If you've seen my video on balancing chemical equations, you'll see what I'm talking about. But anyways, and the other product that you make is the iron, right? The Fe was kicked out essentially, so it's now by itself. And remember, anytime you have a metal alone, it stays neutral. Do not write charges. Do not write any subscripts. This is not a diatomic element. Okay, it's just a metal, so just keep it on its own. Of course, the solid too. And that's a wrap for today. Thank you guys so much for watching. If you found this lesson helpful at all, please don't hesitate to like and subscribe to my channel. It means a lot to me. In our next lesson, we'll be going over double replacement reactions, and that's when we'll really talk about solubility rules and aqueous solutions. So definitely stay tuned for that one. And honestly, if you'd like a full mixed practice video with single and double replacement and combustion problems, just let me know in the comments below. I'd be happy to make one for you. In the meantime, don't forget to check out my community page where I post weekly practice questions. And I hope to see you guys next time in my science studio. But until then, happy studying.